Sorry, I wanted to stop screen sharing. Instead, I pressed stop broadcast. Let's wait a couple of minutes to see if the okay, I think we are all here. We can start again. Okay. So I wanted to show the result of executing the query. So you have this call to MCMH sample. You observe the second argument is the evidence, so the atom yourself. So you observe that for input 1, you get value 3. You got value 3 in the past. And now you want to compute the probability that for input 2, you get value 4. Okay? So this is the query, and this is the evidence. And this is the number of samples to take, 100. P is the probability, and the list of options includes a mixing time of 100. So the first 100 samples are discarded, a lag of 3, and the variables for collecting the number of successes and failures. So by executing, we see that the probability is 0.26, and we got 26 successes and 74 failures, and in fact 0.26 is 26 over 100. You can also ask the same query without with a more complex evidence. For example, in this case, supposing that you observe 2 atoms of evidence. In this case, you can put as evidence a conjunction of atoms. You have to enclose it in parentheses. So you observe that for input 2, you get output. For input 0, you get output 2, and for input 1, you get output 3. You want to compute the probability that for input 2, you get output 4. From this query, we should expect a higher probability with respect to the case before, because if you observe that for input 0 it gets 2, and for input 1 it gets 3, this means that the random function is probably a function that sums 2 to the input. So if it's so, then the output 4 for input 2 is more probable. So if we run this query, we should get a higher probability. In this case, we get even probability 1. We can try again, and again the probability 1. So if we have observed these 2 facts, then the function is surely an addition that adds 2 to the input. Okay, let's go back to the slides. Try not to stop the broadcast. This is for computing the probability, the conditional probability of queries. You can also ask for the conditional distribution of arguments of queries given evidence. So in this case, you can sample arguments of queries by using rejection samplings or metropolis hastings. The API is similar. You provide the query, the evidence, the number of samples, the argument to sample, the list of values, and is returned as output, and you can provide a list of options. For the 2 predicates, the API, the arguments are the same, with the difference that they have a different number of different options. Or there is an error here that I will correct it and put it on. This leg here is not an argument. You can specify the leg with an option. And also you can, as before, draw an histogram of the sample value, and you can also compute conditional expectations. So you want to compute the expectation of random variables conditioned on some evidence, conditioned on having observed some evidence. So cplint offers the possibility of computing conditional expectation with metropolis hastings with the predicate MCMH expectation, and you provide the queries, the evidence, number of samples, the argument to sample, and it returns the expected value. And you can also provide a list of options. So, for example, you can compute the expected values that you get from the function, the random function called with input 2, even that you observe that for input 1, the output was free. So if you go back to the cplint on Swish website, you can compute the conditional expectation here of the output of the random function for input 2, given that you observed 1 and 3. You observed for input 1, output 3. So the expected value is 3, which is close to the value 4 that you would expect if the function was the addition of 2 to the input. So going back to the application, you can see that you can sample, for example, arguments and draw a diagram, an histogram of the sample value. So you can draw an histogram of the values obtained for input 2, given that you observe the input output 1 and 3. So, for example, as you can see, the value 3 is the most common, that over 1,000 samples is obtained in 491 samples. Then 4, 6, 2, 5, 1, 7, in descending order of frequency. And you can also compute expectation using rejection sampling, and you get the correct result, but the process should be slower. So if you take many samples, this should become noticeable. And in this, up to now, we have seen only programs where the random variables have a discrete distribution. They are either discrete constant, or they are integers, and there is a finite number of them. It is possible to use also continuous random variables, and in many cases it's very useful. For example, variables with a Gaussian distribution, or variable with an exponential distribution, or variable with a Dirichlet distribution. There are many distributions for continuous random variables, and with the cplint you can also use continuous random variables, write programs that have continuous random variables. And next week on Tuesday at 5 p.m. CEST, we will see programs with continuous random variables, and in that case exact inference is not available in cplint. You have to use approximate inference, so inference by sampling. And the interesting thing is that for continuous random variables you can nearly reuse the same algorithm as for discrete programs. And after having seen inference and programs with continuous random variables, we will discuss learning, so inducing the parameters and the structure of the rules from data. So I hope to see you next Tuesday. Bye.